All right. Hello, everyone. This evening, we are going to look at section 9.3, in which this will be dealing with exponential functions and graphs. Our objectives are going to be to graph exponential equations and exponential functions and solve application problems involving them. Okay. All right. So the first thing that I want to go over with you is what an actual exponential function is, okay? So if we look here, you will see that an exponential function is going to be in the form of f of x is equal to a to the x power, where x is a real number. So your exponent in an exponential function, your exponent is going to be your variable, usually x, must be a real number. So that means we're not going to be dealing with imaginary numbers or numbers that have negative numbers underneath our radical. Okay, so that is what we mean by has to be a real number. Okay, a, or your base, must be greater than 0, and a cannot equal 1. If we have all of these cases, then we have an exponential function. Okay. Here are a few examples of exponential functions. F of x is equal to 2 to the x power. F of x, or y, is equal to 1/2 to the x power. And then f of x is equal to 3.57 to the x power. Again, take note of, in each of these exponential functions, your exponent is your variable. Okay, how can we graph an exponential function? First thing you want to do is to compute some values. So we are familiar with creating a table. So that means create an XY table. Choose X values. That means choose your numbers that you want to plug in for X, and then plug into the function, and then your output is going to be what Y equals. That is how you create your table, and then you simply plot points and then connect. All right. Let's look at a couple of examples. So example 1 says to graph the exponential function of y is equal to f of x is equal to, of f of x is equal to 2 to the x power. Keep in mind that f of x is the same as y. So to graph this function, we again can choose our values for x. And so when x is 0 and we plug into this function, then what we're getting is, here's my function, y is equal to 2 to the x power. And so if I make x 0, then that's going to be y is equal to 2 to the 0 power, and 2 to the 0 power is 1. Anything to the 0 exponent is going to be 1. So that's where you're getting that from. Excuse me. All right, if we make x 1, then we're saying y is equal to 2 to the first power, therefore y is 2. And that's how we end up with the order pair 1, 2. And so that's all we're doing here to come up with those points. So again, if we're graphing by hand, we create our table, and then we simply take those points and plot them to give us this exponential function. The graph of an exponential function is going to be what we call a J-curve. And so that's what you see here. Things to take note of. If we are looking at an exponential function, as x increases, so that means as x gets larger, y gets larger as well. And so y increases without bound. As x decreases, so that means as x gets smaller, then our y's also decrease, and they're getting closer and closer to 0. We learned about this already, that when your graph gets closer and closer to a specific value, then without crossing, then you have an asymptote. And so in this case, we have a horizontal asymptote of y equals 0. Okay. Also note that the graph is going to go through the y-axis at 0, 1. So we call that our y-intercept. Okay. Let's look at another one. And actually, let me go back for a second. Also keep in mind that if you're being asked to graph, you can also use your calculator. So if we wanted to graph y is equal to 2 to the x, then we type in 2, use our raised arrow, and we get 2 to the x power. Okay, if we want to look at that graph, if we hit zone 6, then you will see the same graph that was created here. If we want to look at our table, you know, the second graph, and you will also see the same table that's been created. So we have negative 1.5. That's what we came up with here, negative 1.5, 0, 1. There's our 0, 1, 1, 2, 1, 2, and so on. And then just keep in mind, if you wanted to come up with some negative points, you just use your up arrow and go up, okay? So that's just a reminder that you can graph by hand, plotting those points, meaning plugging into a XY table, or you can use the calculator, okay? All right, so example 2. This time we have y is equal to 1/2 to the x power, okay? So we can rewrite 1/2 to the x power as 2 to the negative 1 power, okay? If you recall, it's been a moment since we've talked about this, but if we have negative exponents, okay, let me do it like this. If we have 1/2, this is the same as saying 2 to the negative 1 power. Anytime we have a negative exponent, we can get rid of that next negative exponent by moving it to the bottom. And so that's why these are equivalent. And so that's where we're coming up with 2 to the negative 1 to the x power, which is also 2 to the negative x power. So if we were to create a table for that, then we will see that our points look like this, okay? We plot those points, we get a graph that looks like such, okay? Now, take note of here that we have the same points, similar to our 2 to the x, but when we when we create a table for 2 to the negative x, what changes is our x values are now opposites. So instead of 1, 2, we had negative 1, 2. Instead of 2, 4, we had negative 2, 4, and so on. So that allows, let's look at that graph. That allows for this graph to look a little different, okay? A little. And so what we see here is, instead of our graph, our initial graph of 2 to the x, it was increasing. Here, when we have 2 to the negative x, it is now a decreasing graph. And what you should also recognize is that it has reflected over the y-axis. What allows it to reflect over the y-axis is our x, which is inside our function, is now negative, okay? All right, let's keep going. Okay, things to take note of in example 2. Let's go back and look at it. So here's that graph. So as x increases, let's just do it like this, I'm sorry. As x increases, the function decreases. So as x gets larger, our y values get smaller and they approach 0. There's that horizontal asymptote. As our x decrease, our y values increase. The horizontal asymptote is still the x-axis, which is y equals 0. And then our y-intercept is 0, 1. Things I'd like for you to observe by looking at various exponential functions, graphs of various exponential functions. They will always be continuous. Your domain will be negative infinity to positive infinity. Without there being any type of shifts or transformations, your domain, your range will be 0 to positive infinity. Again, as long as we are not shifting okay, you will have a horizontal asymptote at 0, but if we start to shift, then that will change, but we will still have a horizontal asymptote. If your base is greater than 1, your graph is increasing, okay? So like here, bases are greater than 1, 4, 2.5, 1.8, we're increasing. If A, which is my base again, is in between 0 and 1, which these numbers are, in between 0 and 1, that's 0.25, 0.4, 0.7, then our graph is decreasing. Y-intercept is 1, again, provided that we have not done any type of transformation. Okay, all right. So let's recall something. Speaking of those transformations, vertical and horizontal shifts occur when we add and subtract numbers, okay? So remember, let's say we start with our parent function of y is equal to 2 to the x, okay? So if I want this graph to shift up, I can add a number to it. So if I add 5, then that means my entire graph is going to shift up 5. If I subtract 5, that means it's going to shift down. So here we're up 5 units. Here we are shifting down 5 units. Okay, let's talk about a horizontal shift. Okay, horizontal shifts occur within the function. So let's say I said y is equal to 2 to the x plus 5. This time I'm adding 5 inside my function of 2 to the x. And so this is going to give me a horizontal transformation. And if you recall, we talked about when it's inside the function, we do the opposite of what we see. So you would think we were going to move right because of that plus 5, but we would actually shift left 5 units. And then y is equal to 2 to the x minus 5. Again, that 5 is inside the function. So we would move right 5 units. Okay. And then the last type of transformation we're going to talk about are reflections. So if we have y is equal to negative, and then we would have 2 to the x power, then we are going to have a reflection about, oh, I'm sorry, I just lost my train of thought. So a negative on the outside is a reflection across the x-axis. And then if we have that negative inside the function, so this is reflection across x-axis. And then if we had y is equal to 2 to the negative x, now we're inside the function, we are going to have a reflection across the y-axis. And you saw that occur. Oops, sorry, right here. Because this was a negative inside the function. And so it reflected, remember it started this way, and then it reflected about the y-axis because of that negative number. Okay. All right, so let's talk about graphing. So if I was to give you the function, this is example 1. Let's graph, I'm sorry, example 3. Let's graph y is equal to 2 to the x minus 2 power, okay? So we could go to our calculator and type that function in. So 2 to the x minus 2 power. And then we would go to our table and plot some points, okay? And then create our graph. Now, on your assignment that is in my math labs, I want to show you how to do that as well. But before we do that, let's talk about the transformations that occur. So if you recall, our parent function here, or our initial function, is y is equal to 2 to the x. Well, what happened? We have a minus 2 on the inside of the function. So then the transformation that occurs is going to move right 2 units. Okay? What if I gave you y is equal to 2 to the x plus 4 minus 5? Well, if I asked you to graph it, again, you can create your table and plot points. And then let's talk about the transformations. Well, remember, this is that initial function. Now I have a plus 4 inside my function. So that means my graph is going to move left 4 units. Inside, remember, we always do the opposite. And then it would go down 5 units. Okay. All right, so before we move on to the next part, let's take a moment and look at what your My Math Lab assignment is going to ask you to do. All right. So this would be section 9.3. I'm just going to go over here. Mine looks a little different from yours. All right, so this is not the problem that I'm concerned about. You can just use your graphing calculator for that. Here, you're just simply graphing. The ones that kind of get you are the ones in which you have to sketch using your transformations. And so I kind of wanted to go over that with you, okay? All right, so this one says, sketch the graph of the function and check it. Before doing so, describe how the graph of the function can be obtained. So here's my function, y is equal to 2 to the x minus 5. And my choices are A, B, C, and D. So what is happening here? We have a minus 5 inside my function. So that means my function is going to move right 5 units. So if I look down here, 5 units down, nope, right, 5 units, good. So I'm going to choose this one, but then make sure that you understand you need to start here. So we're starting with, remember, f of x is, or y is equal to 2 to the x. So I'm going to put a 2 there. Okay, now I'm going to check my answer. Good job. All right, so now it's time to graph it. So what we are being asked to graph is y is equal to 2 to the x minus 5. Okay, so let's go here. First thing we have to do is choose a tool. Okay, and so this is our exponential function curve. So we're going to choose that. And then we want to save it. Oops, sorry. We choose that. And then now we're going to click our graph to plot the curve. So let's think about a point that we have from 2 to the x. Okay, so if we have 2 to the x, we know that one point, when x is 1, y is 2. Okay, and so now let's think about what has occurred. So we had that minus 5 on, well, let's back up. First of all, what is our base? Our base is 2. So we want to make sure we change that. And then we have a minus 5 on the inside of the function. So as we said, that means that we are going to move right. So we have a horizontal shift, 5 units. Okay, so we have a base of 2, right, 5 units. We're going to save that and let's check it. Okay, and so that's how you would do those problems. You first of all want to, when you go to your graph, make sure you choose the correct base, and then you're going to choose the transformations. Okay, All right, let's keep going. All right, so next. Oops. Okay, so we have the number E. This is a really special number in math. Okay, I say that it's similar to pi because pi is an irrational number, just like E is. Okay, to access E on your calculator, you can do it a couple of different ways. You could do second, the division sign, because when you see above that, you see E. And this is only if you do not have an exponent. Okay, so we won't generally use this one. The other way that we can access E to the X is by, second and then ln, which is your natural log. So if you look above that, you see E to the X. Okay, so again, we're going to hit second, natural log, and we get our E to the X. And so if I'm asking you, let's say to do E to the third, then you would simply put in that exponent as 3 and press enter. So the first example that you were asked to do was to find the value of E to the third and round it to 4 decimal places. So that would actually be 20.0855. Okay, 4 decimal places. So 1, 2, 3, 4. The 3 tells us to stay the same. Okay. There's my B. So E to the negative 0.23. So again, second ln, negative 0.23. Press enter, and I get 0.7945. So let's put that here. 0.7945. Okay, E to the second. So E, so second ln to the second power is going to be 7.389. That 5 tells us to round up. So this time we'll have a 1. So 7.3891. And then the last one is pretty simple. That's just E to the first, okay? So that's just whatever our value is of E. Oops, I got there. Okay, so second ln, and this time it's going to be 1. Okay, so 2.718. Again, we need to round that up to 3. Okay, 2.7183. Okay, almost done. All right, so the graphs of exponential functions with the base of E are very similar to our other exponential functions that have a numerical basis. Okay, if we were to plug in and create a table, it would look like this. So the same thing occurs. If we have an increasing graph with a base of E, if we have a function with a base of E, it's going to be an increasing graph. If that exponent is negative, it's going to be a decreasing graph. Okay. And then if we wanted to graph this on our calculator, we would simply go to y equals, and then so if we wanted to graph the function of E to the X, we can type second ln, and then we change that, we make that exponent the variable X, and you'll see your graph. Okay. All right, last thing. All right, so compound interest. Okay, compound interest is a tool that we can use to determine the formula, is a tool that we can use to determine the amount of money that we would have if we were investing it or if we owe, and we are trying to determine the interest that is going to be accumulated and added to that amount. Okay, and this is the formula that you would use. So we have A is equal to P times 1 plus R over N, all to the NT power. Okay, and so let's talk about what these variables represent. So first of all, your P represents your principal. Your principal is always going to be that starting amount, whether it's the amount that you have invested or maybe the amount that you have taken out in a loan, okay? Your R in this formula is going to represent your interest rate. And always want to remember that this is going to be a percentage. And so before you plug into your formula, you want to make sure that you take it out of percent form. And you can do that by dividing by 100 or simply moving your decimal 2 places to the left. And then N is going to represent, that's the N here, the number of times it's going to be compounded. And you'll see that in just a moment. If in the problem it says it's being compounded annually, this is how much it's going to be compounded, the number of times compounded in a year. So if we're saying annually, then that means your N is going to represent 1. If it's saying it's being compounded semi-annually, then your N will equal 2. Quarterly, N will equal 4. Monthly, N is 12. And then daily, your N is 365. Again, keep in mind that this is the number of times it will be compounded within a year. And so that's where these numbers are coming from, okay? All right, so final example for the evening. Says, suppose that $100,000 is invested at 6.5% interest compounded semi-annually. We're going to find the function for the amount in which it's going to, to which the investment grows after T years. And then part B, we are going to find the amount. All right, so we want to find the amount of money in our account at T equals 0, T equals 4, T equals 8, and T equals 10 years, okay? All right, so let's do it. So here's our formula, and we're simply gonna plug into it. So for part A, our A is going to equal P. So in this case, our P is our principal, which is 100,000, times 1 plus R. So in this case, my R, my interest rate is 6.5%. So we can, remember, we have to take that out of percent form. So we could say, all right, 6.5 divided by 100, which gives us 0.065. Or, as I told you before, you can take that decimal and move it 2 places to the left. And so we get the same thing, 0.065. So 0.065 over N, all right? It's telling us it's being compounded semi-annually. So that means my N is 2. So 0.065 over 2, close parentheses. My exponent is going to be 2. And then T, I don't know T because it says T years. So I leave that as my variable. And so this is my function, okay? Then part B. Part B says to find the amount of money in our account at each one of these times. So we simply plug into our formula. All right, so here we go. So we're going to say 100,000. There it is. Okay, that's better. So we're going to say 100,000 times, open parentheses, 1 plus alpha y equals, to get our fraction, 0.065 On the bottom, we have 2. Make sure you arrow out of that and close your parentheses. And now we need our exponent. So you're going to use your raised arrow bar. And then we're going to have 2, but this time my t is 0. So 2 times 0. And I get, oops, I didn't put 100,000, I put 10,000. So I'm going to arrow up. Let's arrow over. Instead of retyping all this, I'm just copying and pasting. And I just need to add a 0. So instead of deleting, I'm just going to hit second delete, which allows me to insert, and I just add a 0. So now I have, 100,000. And so my answer is 100,000. So when t is 0, I'm going to have $100,000. All right, so the next one we were being asked was when t is 4. So I'm going to be lazy, and I'm just going to simply go up again and copy and paste. So you just arrow up on top of it and press enter. And the only thing I needed to change is my t. And so I'm going to use my left arrow and simply get on top of 0 and change it to 4. And so now I have $129,157.75. Make sure you're rounding correctly. We're talking about money. So we round to 2 decimal places. Okay. And so then the other 2 is when t is 8 and when t is 10. So you can work those on your own, and then these are the answers that you should get, okay? So when t is 8, you should get $166,817.25. And then when t is 10, you should get $189,583.79. All right. That concludes our lesson on section 9.3. Have a good evening.